Welcome to the world of combinational logic design. In this video, we'll explore how digital systems process information using logic circuits. Combinational logic forms the backbone of digital electronics, enabling devices to perform calculations, make decisions, and manage data. Whether you're a student, an engineer, or simply curious about how computers work, understanding these concepts is essential. We'll start by looking at the standard ways to represent Boolean functions, then move on to powerful simplification techniques, and finally, we'll dive into the most common combinational circuits and their real-world applications. Let's begin our journey into the fascinating realm of logic design. The heart of combinational logic lies the Boolean function. Boolean functions use logical operations like and, or, and not to describe how inputs relate to outputs. These functions are the mathematical language of digital circuits, allowing us to predict and design circuit behavior. By representing logic with Boolean expressions, we can systematically analyze and optimize circuits for efficiency and reliability. In the next scenes, we'll see how these functions are commonly represented to make design and simplification easier. One of the most widely used forms for representing Boolean functions is the sum of products, or SOP. In SOP, we express the function as a sum OR of multiple product and terms. Each product term corresponds to a specific combination of input variables that produce a true output. This format is especially useful because it directly maps to the implementation of logic circuits using and OR gates. SOP is intuitive, easy to read, and forms the basis for many digital designs. Another standard way to represent Boolean functions is the product of sums, or POS. In this form, the function is written as a product and of several sum OR terms. Each sum term represents a condition where the output is false, and the overall function is true only when all these conditions are met. POS is particularly useful for certain types of logic simplification, and is often used in the design of circuits where NOR and NAND gates are preferred. Both SOP and POS are essential in digital logic design, but they serve different purposes. SOP is generally more straightforward for implementing circuits with and OR gates, while POS is advantageous when using NOR and NAND gates. Understanding when to use each form can lead to more efficient circuit designs. As we move forward, you'll see how these representations play a role in simplifying and implementing complex logic functions. Simplify Boolean functions. Engineers often use Karnaugh Maps, or K-maps. A K-map is a visual tool that helps identify patterns and redundancies in logic expressions. By organizing truth table values into a grid, K-maps make it easy to spot groups of ones or zeros that can be combined, leading to simpler and more efficient circuit designs. K-maps are especially useful for functions with 2 to 6 variables. Start with the simplest K-map, 2 variables. The grid has 4 cells, each representing a unique combination of the 2 input variables. By filling in the cells with output values from the truth table, we can quickly identify adjacent cells with the same value. Grouping these cells allows us to simplify the Boolean expression, reducing the number of gates needed in the final circuit. With 3 variables, the K-map expands to 8 cells. Each cell corresponds to a unique combination of 3 input variables. The process remains the same: fill in the cells with output values, then look for groups of ones or zeros. These groups can be pairs, quads, or even octets depending on the pattern. The larger the group, the simpler the resulting Boolean expression. 4-variable K-map contains 16 cells arranged in a 4x4 grid. This allows for even more complex functions to be simplified visually. By grouping adjacent cells with the same output, we can minimize the logic expression, often leading to significant reductions in circuit complexity. K-maps are a powerful tool for both students and professionals in digital design. In dealing with 5 variables, the K-map grows to 32 cells, often represented as 2 4x4 grids. Although more complex, the principles remain the same. By systematically grouping cells, we can still achieve significant simplification. This is especially useful in larger digital systems where minimizing gate count is crucial for performance and cost. For 6 variables, the K-map contains 64 cells, typically arranged as 4 4x4 grids. While this can be challenging to manage by hand, the visual grouping technique still applies. In practice, software tools are often used for such large K-maps, but understanding the underlying principles helps in troubleshooting and optimizing digital circuits. In simplifying with K-maps, it's important to follow grouping rules. Groups must contain 1, 2, 4, 8, or any power of 2 cells. Each group should be as large as possible, and groups can overlap if it leads to further simplification. This approach ensures the resulting Boolean expression is as simple as possible, reducing the number of gates in the circuit. Let's walk through a quick example. Suppose we have a 3-variable function with certain outputs set to 1. By plotting these on the K-map and grouping adjacent ones, we can derive a much simpler Boolean expression. This process not only saves time but also leads to more efficient hardware implementations. For functions with many variables, manual simplification becomes impractical. The Quine-McCluskey method is a tabular technique that systematically finds the simplest form of a Boolean function. It's especially useful for computer-based minimization and can handle more variables than K-maps. Let's see how this method works in practice. First step in the Quine-McCluskey method is to list all minterms of the function in binary form. Each minterm represents a unique combination of input variables that produce a true output. By organizing these minterms, we prepare for the next stage, combining terms that differ by only one variable. Next, we group minterms based on the number of ones in their binary representation. This grouping makes it easier to identify pairs of minterms that can be combined. By systematically comparing and combining these pairs, we reduce the number of terms and move closer to the simplest expression. After grouping, we compare minterms in adjacent groups and combine those that differ by only one variable. This process is repeated until no further combinations are possible. The remaining terms are called prime implicants, which are essential for constructing the minimal Boolean expression. Once all prime implicants are identified, we use a prime implicant chart to select the essential ones. This chart helps visualize which prime implicants cover each minterm. By choosing the minimum set that covers all minterms, we achieve the simplest possible Boolean function. Quine-McCluskey method is a powerful tool for logic minimization, especially when dealing with many variables. While it can be time-consuming by hand, it forms the basis for many computer algorithms used in digital design today. Mastering this method gives you a strong foundation for tackling complex logic problems. Now that we've covered Boolean function representation and simplification, let's turn our attention to combinational circuits. These circuits produce outputs based solely on their current inputs with no memory of past states. They form the core of digital systems, performing arithmetic, data routing, and decision-making tasks. Let's explore the most common types of combinational circuits and how they're used. Adders are fundamental combinational circuits used to perform binary addition. They're found in everything from simple calculators to advanced processors. There are two main types, half adders and full adders. Each type plays a unique role in digital arithmetic, enabling computers to perform calculations quickly and accurately. A half adder is the simplest adder circuit. It takes two single-bit binary inputs and produces a sum and a carry output. The sum represents the basic addition, while the carry indicates if the result exceeds 1 bit. Half adders are the building blocks for more complex arithmetic circuits. Full adder extends the concept of the half adder by including a carry-in input. This allows it to add 3 single-bit numbers, 2 inputs, and a carry from a previous stage. The full adder outputs a sum and a carryout, making it possible to chain multiple full adders together for multi-bit addition. Adders are used in a wide range of digital devices, from simple counters to complex processors. They enable computers to perform arithmetic operations, process data, and execute instructions. Understanding how adders work is crucial for anyone interested in digital system design. Subtractors are another essential combinational circuit. As the name suggests, they perform binary subtraction. Like adders, there are half and full subtractors, each designed to handle different scenarios. Subtractors are vital for arithmetic operations in digital systems. Half subtractor takes 2 single-bit binary inputs and produces a difference and a borrow output. The difference is the result of the subtraction, while the borrow indicates if the first input is smaller than the second. Half subtractors are used in simple arithmetic circuits and as building blocks for more complex designs. A full subtractor handles 3 inputs, 2 binary numbers and a borrow-in from a previous stage. It outputs a difference and a borrow-out, allowing multiple full subtractors to be connected for multi-bit subtraction. Full subtractors are crucial for designing arithmetic logic units in computers. Subtractors are used in digital systems for operations like calculating differences, managing counters, and implementing arithmetic logic units. Their ability to handle binary subtraction efficiently makes them indispensable in modern electronics. Multiplexers, or MUX, are combinational circuits that select one of several input signals and forward it to a single output line. By using selection inputs, a MUX can route data from multiple sources to a single destination. Multiplexers are widely used in communication systems, data routing, and digital control circuits. Multiplexer operates by using selection lines to choose which input is connected to the output. For example, a 4-to-1 MUX has 4 data inputs, 2 selection inputs, and 1 output. Depending on the selection input values, the MUX forwards the corresponding data input to the output. This flexibility makes multiplexers essential for efficient data management. Multiplexers are used in a variety of digital systems, including communication networks, memory management, and data selection circuits. Their ability to efficiently route data makes them a cornerstone of modern electronics, enabling complex operations with minimal hardware. Demultiplexers, or DEMUX, perform the opposite function of multiplexers. They take a single input and distribute it to one of several output lines based on selection inputs. DEMUX circuits are essential for distributing data from a single source to multiple destinations in digital systems. Demultiplexer uses selection lines to determine which output line receives the input signal. For example, a 1-to-4 DEMUX has 1 data input, 2 selection inputs, and 4 outputs. Depending on the selection values, the input is routed to the corresponding output. DEMUX circuits are widely used in data distribution and communication systems. Demultiplexers are found in digital communication systems, memory addressing, and data distribution networks. Their ability to efficiently direct data from a single source to multiple destinations is crucial for the operation of complex electronic systems. Encoders are combinational circuits that convert multiple input lines into a smaller number of output lines, typically representing binary codes. They are used to reduce the number of wires needed for data transmission and to encode information efficiently for processing. An encoder takes several input lines, only one of which is active at a time, and generates a binary code corresponding to the active input. For example, a 4-to-2 encoder converts 4 input lines into a 2-bit binary output. Encoders are widely used in keyboards, data compression, and digital communication systems. Encoders are essential in digital systems for tasks like keyboard encoding, data compression, and efficient data transmission. By converting multiple signals into compact binary codes, encoders help streamline communication and processing in electronic devices. Decoders perform the reverse operation of encoders. They take binary input codes and activate one of several output lines. Decoders are crucial for tasks like memory addressing, data selection, and display systems in digital electronics. Decoder receives a binary input and activates the corresponding output line. For example, a 2-to-4 decoder takes a 2-bit input and activates one of 4 outputs. Decoders are used in memory systems, display drivers, and data selection circuits, making them vital for digital design. Decoders are widely used in memory addressing, enabling computers to access specific memory locations. They also play a key role in display systems, where binary codes are converted into signals that drive individual segments or pixels. Their versatility makes them indispensable in digital electronics. Comparators are combinational circuits that compare two binary numbers and determine their relationship. They output signals indicating whether one number is greater than, less than, or equal to the other. Comparators are essential for decision-making processes in digital systems. Comparator takes two binary inputs and produces outputs that indicate their relationship. For example, a 2-bit comparator can determine if one input is greater than, less than, or equal to the other. Comparators are used in sorting, decision-making, and control systems across digital electronics. Comparators are found in digital systems for tasks like sorting data, controlling processes, and implementing arithmetic operations. Their ability to quickly determine relationships between numbers makes them a key component in many electronic devices. Combinational circuits are everywhere in modern electronics. They're used in arithmetic logic units, data routing, memory addressing, signal processing, and much more. Their speed and reliability make them the foundation of digital systems, powering everything from smartphones to supercomputers. This video we've explored the essentials of combinational logic design, from representing Boolean functions with SOP and POS, to simplifying them with K-maps and the Quine-McCluskey method, and finally, to understanding the key combinational circuits and their applications. Mastering these concepts is crucial for anyone working with digital systems. Thanks for joining us on this journey through the building blocks of modern electronics.